Hello everyone, I am Harish. In this tutorial we will see how to perform some common quantum espresso calculations using a Python package called QETools. So first, to check the software is installed or not, you need two softwares, Quantum Espresso and QETools. So if you are on Linux, just type which pw.x. So I installed it is already installed in my system. If it is not in your system, you can just install. If you are using Ubuntu, this command will install. And next thing we have to install is QETools. So for QETools, we can just search the QETools pipe in Google. So this is the page. So command line helper for quantum espresso calculations, you can get this, and description is given, all the tags and how you can calculate the properties using quantum espresso. So you can check out all the tags here. We will be using this software. So this is the command to install this software. Okay, so to check whether you install that or not, just type QETools. So we have QETools in my system. Otherwise you can just install using pip install QETools. Okay, so since we have all these softwares, so advantage of QETools is it will download all the pseudo potential files. So you can use PBE, Soul, LDA by default. Otherwise you can give your own, and these type of calculations it will done on its own with minimum human intervention. So for using QETools, we need just structure file. Here I have a silicon structure. If you see the contents, so it is 2 atoms unit cell, which is primitive diamond cubic. So when you have the structure, first thing we have to do is the convergence studies. What is the converged NCAT, what is the converged K-grid, or something like that. So first we will do some NCAT convergence. For that, command is this calculation. By the way, you can get all the tags by default, like H is for help for any command. So you can get all the tags, what all means, something like that. So here these are all calculations we can perform using this QETools. So first we do NCAT convergence. So calculation is NCAT. What is structure file? silicon.cif. So PPD you can give, PBE you can give. These are already downloaded. PB Soul you can give, and LDA you can give. So these are already downloaded. Otherwise, if you want to give your own pseudo potential files, just give the path of those pseudo potential files. For example, this is the directory. This is the directory in which pseudo potentials are there, and the pseudo potential have to be in the form of element, whatever the element is in our structure, all the elements dot UPF. So this is the format for which this script will search. Okay, so from wherever you can download the UPF files or whatever the pseudo potential files and rename them to element.upf. So the script will search in that given directory. So I want to use PBE for this calculation, and it is default, so I am not using it. And PPN is a number of nodes, it is 6. It will take some default value. It's better to give PPN every command. So it is doing NCAT convergence studies. So it is done. If you see, it has written one file, convergence data. If you see what is that file, so it is, so I think 50 is good. So after 50 there is no much change. I am going to use 50 for further calculations. So the next calculation is K-grid. Okay, K-grid I am using converged NCAT, which is 50, and file is same. PPN I am using 6. Okay, so it will do the K-grid convergence. This K-grid convergence will only work for the cubic structures, because we cannot so the generating that incremental K-grid is difficult. So if it is non-cubic structure, it's better to do manual SCF calculations at each required K-grid. So this will work for cubic because it just multiplies. Okay, so now we have K-grid data also. So here I think 8 is good to go. After it there is no much change. So after convergences, what we have to do is relaxation. So I want to do VC relax, converge n cut of 50, converge k grid of 888, file is same silicon.cif, and number of nodes I want to use is 6. Okay, so it will perform the VC relaxation. It will take 1 or 2 minutes, depends on the number of atoms and processors. So it is done. Just check for the pressure and forces. Pressure is 0, forces are 0, so it's very good. So now we completed the relaxation also. If you see what happened in all these calculations, if you go to ncut folder, there are all ncut files. So go to 30. So this pw.i, so this espresso.bwi, this file is written by QETools, which is the input file for the quantum espresso. This is the output file. These are the save files and XML files. Okay, so if you see the input file, so here we are using 30 as Eichert wave function. These are the pseudo potentials by default, which comes with the QETools. Okay, and K points we are using 444. si.upf is the pseudo potential file. Okay, so this is how it works. It creates all input files and it runs the calculation on its own. So after this we don't need these ncut and kgrid folders. So we have relaxed structure. So after relaxation, one thing we have to do is SCF calculation with all the parameters. So QETools, what are the calculation we want to do? SCF with 50, kgrid is 888. Right now file is relaxed file, VC relaxed at espresso.bw. So we are using relaxed structure, ppn of 6. Okay, so it does the SCF calculation. So if you see the force and pressure is negative, okay, these are negligible numbers. So we have, right now we have the SCF folder. This is the main folder for further calculation. So what are further calculations? If you again check the help, what are all you can do? So ncut we did, kgrid we did, vacuum we don't need for bulk things, VC relax we did, SCF we did. NSCF is like, it uses the charge density of SCF, but it can calculate the eigenvalues on finer grid. Like SCF you use 888 k grid, NSCF you can use 20 20 20. It won't calculate the charge density, it will use the same charge density to calculate the eigenvalues at all these grid points. Band is simple band structures, DOS is density of states. Pressure is, if you want silicon structure which is at 20 gigapascals pressure, so we want that structure, so that we can go by isotropic compression. EOS is equation of state, and harmonic is if you want to displace an atom in one direction, what is the displacement versus energy diagram, that is harmonic plot. pH pre, pH mid, pH post, these are for phonons. After pH post, that means you completed all the phonon related calculations. pH bands is for band structure, DOS is for density of states. EPW we are not going to discuss in this video. So this is for all these calculations. After SCF you need a completed SCF calculation. Okay, NSCF, bands, DOS, pressure you don't need, EOS you don't need, harmonic I think we need. So per pH, so for this we need SCF calculation. Okay, so right now we have SCF. Just do bands calculation quickly. So what is the calculation? Bands, and file is same, relaxed file. So for band structure, if you know, we have to give the band path, particular K band path. So these band paths I am reading it from ASC file. So ASC is a very good website. It is called Atomic Simulation Environment. So it can give a lot of things. So IO for the structure files also in this tag. So these are also read by ASC only. So if you see IO, ASC.io, all these files, all these formats it can read. It can read CIF, it can read castep, it can read evinit, it can read a lot of things, espresso, in, out, wasp, something like that. So bandpath also I'm getting from that package. Okay, so I'm using the default default bandpath. So it is calculating band. So by default it will calculate for 200 points. You can change that using nq command. So it printed Fermi energy. So we can change here, if you see it is done for 200 points, you can change it to 100. So nq is for number of q points. Right now we completed band structure. If you do ls, it is the band structure which is plotted. So just open that. So this is the band structure. Okay, so this is zero energy, it is by default it is drawn. So this blue line is the Fermi energy. Okay, if you see that no band is touching that Fermi energy line, that means it is semiconductor or insulator. Okay, this is the electronic band structure. So we have band structure. The next thing we need is DOS. Let's perform DOS also. For DOS we can give cursor grid. Calculate this DOS, same structure file. It will take very least amount of time. So DOS is also done. If you see DOS.png, it is created. If you open that, well, this is DOS. See, it is showing density of states at Fermi energy. So this black line is Fermi energy, but there are no bands in the band structure. It is because of brilliant zone summing. So we need brilliant zone summing to be tetrahedra. By default it will be, if you see the input file, here it is not written. By default it will be smearing. We need, so just create a file. The parameter is bjet sum. We want to use tetrahedra. Okay, save this file. When we calculate the DOS, give that parameter file. So par is for parameter file. It will read this file. I think it will give some error because we use smearing in the SCF calculation. So let's do one NSCF calculation with these parameters. K grid is, let us say, let's use 12 12 12 in this parameter. Okay, earlier it did not work because we used the smearing in SCF, and here we are using tetrahedra. I think right now it will work, the DOS calculation. K grid we can use as 12 12 12. We use it in, for DOS it is good to use finer grid. First do one NSCF calculation and do the DOS calculation. So here we are using tetrahedra. Tetrahedra will take a little bit of time. It is done. If you see, the DOS is there. So right now there is gap. See, there is gap. It will be around 1 electron volt or something. So experimental thing is 1.1. It is around that. So now we have all. We have band structure, we have relaxed structure, and we have the DOS also. Let's do equation of state. Okay, so what is the energy? 50. What is the K grid? I use 888. What is the file? Use relax espresso.pw. How many processors? Let's use 6. So this will fit the equation of state. It's like volume versus energy plot basically. So, and it will give the what is the minimum value at which energy is, what is the value at which energy is the minimum, and it will give the bulk modulus also, because bulk modulus is nothing but dou square u by dou v square something. So it does some points. I think default is 10 such structures. We can change that number also. So it's done. UOS. So all these things will be in UOS folder. Let's see how many structures it did. So it did, I think, 10 structures. Okay, this is the ratio of relaxed volume to the original volume. So just open UOS.png. So this is the UOS, and bulk modulus, if you see, 85.475. Let's check whether it is around silicon bulk modulus. So 95. Silicon bulk modulus 95. We are like almost there. Okay, that is one thing. So we plotted UOS also. We plotted band structure, we plotted DOS, and we plotted UOS. Now let us say we want silicon at 20 gigapascals, right? So some calculations need at high pressures. So for that we have to do the pressure tag. QETools, calculation is pressure, ncut is 50. We use the same. Kgrid is, here we use a little bit small because it will take a lot of number of calculations. In regular calculation we have to give the same thing. So ppn I am using 4. That's it. And what is the required pressure? These are the important tags. We have to give them in kilobars. 1 kilobar, I think 10 kilobars is 1 gigapascals. So if you want 10 gigapascals, let's give 100 kilobar. Initial compression, the way it works is like it will compress the cell by this ratio, and when this compression happens, that pressure should be more than required pressure. Then it will do bisection method to reach the required thing. I think initial compression is 0.9 default. I think 0.9 is enough here. So if you run this, so I forgot to give structure file. Structure file is vcrelax.espresso.pwo. So 0.9 is the default. So it will use bisection method to reach that value. So if you see the pressure 99.37, so it is doing, yeah, right now it is done. ls, there will be a file called pressures, so it will give the all the information. Cat pressures, so this is the compressions and pressures and all. So with this compression it reached 100 kilobars. And what is that structure? Pressure.in. This is the quantum espresso readable structure, so it will write that structure. If you do pressure.in, so these are the positions and these are the cell values. So we have the pressure structure at liquid pressure. It is at 10 gigapascals and 100 kilobars. So that is how we can use it for generating compressed structures. Another thing is harmonic. We want to see if you displace an atom little bit from its equilibrium position in a given direction, how the energy will change. So those can be carried out using harmonic tag. Harmonic. So we use same these things. Kgrid, I want to use less number because it will do a lot of calculations. And what is the atom ID? I want to use 0. What is direction? Displacement direction. Let's say x. In silicon all are same, so use ppn6. Okay. And what is the structure file? vcrelax.espresso.pwo. I think it also does like 10 calculations for plotting the energy versus the displacement plot. Let it complete. We gave the small cake, so it should be fast. It is taking some time. Okay, now it's done. So if you see, there is a folder called 00 harmonic, 0th atom in 0th direction. So if you see what all it does, so it calculated I think 10 different compressions, okay, different displacements. So you should be seeing the plot also, harmonic.png, and that. So this is the harmonic plot. It is almost harmonic. This E2, it is the second order force constant kind of thing with that for that atom. And first E1 is the first derivative, it will be 0 because we are using relaxed structure. E2 is the second derivative. 3 is also 0 because there is very less anharmonicity here. Okay, so this is the use of harmonic calculation. We can do it for any atom in any direction. Okay, right now we are all done with the electronic calculation. Let's start phonon. Okay, in the electronic part we relaxed the structure. We know the structure with 0 pressure and 0 forces. We found out the bulk modulus and equation of state. We calculated the band structure. We calculated the density of states, and we calculated the harmonic properties. It's not harmonic properties actually, it's fitting harmonic potential for that particular atom in that particular direction. So our phonons, again you need this SCF folder already in this. So let's start phonon calculation. QETools calculation is pH pre. This is mandatory. So NCAT and K grid is not mandatory for this. This K grid is Q grid for phonons. Okay, I want to use very less number, 444 let us say. The file is same, espresso.bw, ppn is 6. Okay, so I am doing pH pre. It will calculate all the, so for 444 we have to calculate 13 individual Q points and 2 atoms, so it will take little bit of time. And so once you are done with the pH pre, so you will see the phonons folder, everything will be in that folder. After that you can choose 2 methods. One is doing pH mid. Calculation is pH mid with the K grid of 444, same as pH pre, and it is, I think NCAT doesn't matter here. File is same as the pH pre, ppn 6. So here also you can use this tag var. You can give all the parameters which are in the pH.x input description. We can simply write that file and give the parent that file. Right now I am not using anything. So if you do this pH mid, so it will, so sorry I forgot underscore. If you do this, it will automatically start. The thing it does is, if you go to phonon, it writes all these in files, ins and start files, and one script file. Right now actually it started working. In general it won't happen in the updated package. So if you see the pH script, so for all the, in all Q points, so it will check whether start is there and it will run, okay, on 6 nodes. The advantage of this is, this script you can run it on different CPUs at the same time. So if pH 1 is running, mid 1 is running, and you are running this script in another system, because there will be start file for one, it will start the mid 2, something like that. So if you want to use multiple computers, multiple jobs for the same, because these phonons will take some time, if you want to use multiple jobs, you can just give pH mid and run this script file, so that will work. Otherwise we can just do with the pH post directly. After this mid also you have to run pH post, that will combine all the calculations. You can directly start pH post, so it will just start the calculation, but these Phonon calculation, they will take some time. So for that I have already completed this Phonon. Let me, what are the processes are running. So there are a lot of processes, let them kill. L313 272 30 13 272 32. So I think yeah, right now they are dead. Okay, so I already performed these Phonon calculations here. If you go to Phonon's folder, so I already done all these calculations. Okay, after this Phonon post ph post calculation, you will have a file called harmonic flfrc.dat. This is all we need from this. Okay, and after calculating that ph post, so we can do that now also. So what is the calculation? Ph post, assume that I completed all the pH mid calculations. Okay, so k grid, I need to know what is the k grid I used here. So k grid I used was 666. Okay, I have to use the same k grid here also. K grid is 666. What is the file? I think relax.pw. Okay, ppn I am using 6. So I think it will run because it is already completed. It is just reading the files from already completed jobs. This is what happens every time. So after reading all these ph files, it creates the, if you go to Phonons, so it did all the data files. These are all will be in SCF folder only. So it created harmonic flfrc.dat file. Okay, this is what we need. So once we have that harmonic flfrc file, we can plot Phonon bands using QETools calculations pH bands. Okay, this is the band path we can give, but I am using AAC. What is the file? relax.pw. This file will be used for creating band path, and let's use ppn to be 6. Okay, I think it should be able to calculate. pH bands is done. So these bands will be written in Phonon's folder. Okay, so here Phonon bands svg. If you open that, so these are the Phonon bands. Okay, so as usual, x-axis is centimeter inverse, the default unit of quantum espresso. And this is the Phonon's band structure. If you want to calculate DOS, Phonon DOS, same thing, it will calculate. So since I am in Phonon's directory, I have to come out. So you should always be in the directory where SCF folder is there. Okay, because it reads a lot of information from that SCF folder. If I run the job, it will take some time. DOS. So it is done. The file will be created in Phonon's folder. If you see ph DOS. Okay, if you open ph.svg, so this is the Phonon density of states. So these are 0 and 1 are the unique atoms in the structure, the number of atoms. So they are actually same atoms because it is symmetries does that, so that's why they are superimposed. Black is the total density of states and this is the partial density of states of those particular atoms. Okay, that's it. So we did all band structures, density of states. Again, if you check in the help tag, these are all tags I think we used except T. T is like when you are doing pressure calculation. So what is the difference you want? So if you want 100 kilobars, so you want what is the precision, like 100.001 is okay or not. So that is the threshold. You can give just 0.1. I think that is the default. So vacuum direction, when you are using 2D materials, it is necessary to give the vacuum direction, in which direction 1 2 3 x y g. Okay, so we did all the calculation. N pool is for EPW calculations. ASR is Phonon band structures, atomic strict sum rule. So we can give the value for pH.x. I think simple is the default value. Emin and Emax, for some materials the band structure will be like very closed, so there will be a number of bands and you don't see that Fermi level clearly unless you zoom that. So for zooming we can give the what is the minimum and what is the maximum values you want in band structures. Okay, so this is it. So if you see this PyP documentation page also, you will get a lot of information. So I request you to kindly use, if there are any issues, just feel free to write to me. This is the mail ID in PyP page. Yeah, thank you.